In 1988, I wrote a popular science book called A Brief History of Time, which sold over 10 million copies. I say that not to brag, but to underline the deep fascination we all have with our universe.
20 years ago, people rushed to buy Stephen Hawking's book. It was an unlikely sensational bestseller, and he became an instant celebrity. In the book, he promised we would soon have the ultimate answer, a theory of everything that explained how the universe began. But 20 years on, it remains tantalizingly elusive, and Hawking's body is deteriorating. Now his only way of communicating is through one muscle in his cheek. For Hawking, time is running out to unlock the mysteries that could finally make him master of the universe. These films are a journey into the extraordinary quest for a theory of everything.
Let's go.
He does not see himself as a genius. He sees himself as one of those lucky people who get paid to do what they love. It's just that his job is a little bit different from most people's. "20 years ago, Hawking said he wanted to know the mind of God. He felt he was on the brink of delivering a simple, elegant set of laws that would explain everything in our universe, and more importantly, how it all began.
How can we understand the universe? Is it arbitrary, or is there a grand design? Do we still need a God? 20 years on, my need to find answers to the fundamental questions about our existence is undiminished.
Hawking's need to find answers started early. He was born in 1942, during the darkest days of World War II. Hawking has always enjoyed the fact that he was born 300 years to the day after the death of that other revolutionary scientist, Galileo.
How true is it that when you were first diagnosed that you listened to Wagner and drank heavily?
I took to listening to Wagner, but reports in magazine articles that I drank heavily are an exaggeration. The trouble is, once one article said it, other articles copied it, because it made a good story.
The outlook was bleak. Motor neuron disease is progressive. The nerves controlling the muscles degenerate to complete paralysis, while the brain remains intact. He was given 2 years to live. Before then, as a student, Hawking had, by his own admission, become somewhat directionless. Now faced with an uncertain and nightmarish future, he developed a fierce determination that would become his hallmark. Often to the exclusion of all else, he set his sights on the greatest questions in physics. Professor Bernard Carr was a graduate student of Hawking's and became his close colleague.
And of course, it's required a huge amount of effort for him. But it's, in some sense, I think, given Stephen the determination to overcome the problems, and it made him even more determined, I think, to sort of, to crack the ultimate problems of physics.
Wanted to get an idea of what the beginning of the universe looked like, but to do that, he'd have to attempt what everyone else thought was impossible. Einstein's theory of relativity is the theory of the very large, of planets, galaxies, and space. Quantum mechanics is the theory of the very small, of atoms, particles, and forces. But to understand how the universe came about, Hawking would have to force the two together.
My life's work has been to unify the theories of the very large and the very small. Only then can we answer the more challenging questions. Why are we here? And where did we come from?
It's a quest that, despite near total paralysis, he's not about to give up on.
He's a very tenacious, courageous individual, but he never thinks of it like that. He just gets on with it. That's really how he gets on with everything.
Asked how did it all come to be, we don't have one single answer, yet. Can I have a minute, please?
Stephen Hawking is the Lucasian Professor of Mathematics at Cambridge University, a post once held by Sir Isaac Newton. Age 66, Hawking still tirelessly puts in a full week of teaching and research. Hawking's schedule is frantic. As well as trying to find out how our universe came about, he tries to satisfy an incessant demand for his illustrated lectures.
Can you hear me? According to the Bashango people of Central Africa, in the beginning there was only darkness, water, and the great god Bumba. One day Bumba, in pain from a stomach ache, vomited up the sun. The sun dried up some of the water, leaving land. Still in pain, Bumba vomited up the moon, the stars, and then some animals. The leopard, the crocodile, the turtle, and, finally, man. This creation myth, like many others, tries to answer the questions we all ask. Why are we here? Where did we come from?
His groundbreaking work catapulted Hawking out of his depression.
I certainly remember Stephen in lectures asking extremely awkward questions at the end of seminars or in the course of seminars. That was the thing that struck me particularly about him. Very penetrating questions, I should say, not just awkward.
Penrose had given Hawking a glimpse of how physics could be used to answer the question, why are we here? For both Penrose and Hawking, the starting point was Einstein's theory of relativity, the theory of the very large.
I know that the universe is sprinkled with galaxies, and I really mean sprinkled. There's a lot of empty space around each galaxy. Let's take our galaxy, the Milky Way. It would comfortably fit in a full stop in Stephen's book.
Our galaxy is microscopic compared to the gigantic tracts of empty space that dominate the universe. But Einstein showed that all that empty space turns out to have some remarkable properties.
Let's imagine that this basketball is a celestial object like a star, okay? And let's imagine that this bookshelf with these books is space. In our classical view of space, it would be rigid like this. It would just be this static thing, this thing that is unresponsive. But in our modern view, this star, as it moves through space, it warps it, it dents it, it bends it. And other objects that then move through this space will feel this warp, will feel these bends, these warps, and will move according to that. They won't move in straight lines. They'll feel these bends and they'll curve.
The fact that big objects like stars can actually bend and curve space is now an everyday notion to astrophysicists like Kim Weaver.
What we're talking about in terms of astronomy and cosmology are objects that have a huge amount of mass. A planet-sized object, or a moon-sized object, or a star-sized object. The mass of this object bends space around it. If the ball here that is at the center of the sheet is representing the sun, and this penny is representing a planet like the Earth, then you can use the penny to demonstrate how the Earth orbits the sun.
Most of us think of gravity as an invisible force which holds us on the Earth and keeps the Earth in orbit round the sun. So far so good. But what physics says is really happening is that planets are trapped in areas of curved space. The Earth is actually rolling round and down into an area of space warped by the sun. The penny rolls in quickly, but of course it will take the Earth billions of years to hit the sun. And it's the curvature of space caused by the Earth itself which holds us in place on our planet. Something that was many times bigger than our sun is compressed to a size smaller than an atom. It becomes so incredibly dense that it pulls space back towards it. Everything in that warp space is eaten up. Even light cannot escape its clutches. Around the ultra-dense centre, there forms a sphere of darkness that we now call a black hole. Was that Penrose had proved, using Einstein's equations, that at the very centre of a black hole there had to be a plug hole, down which matter, space and time disappeared. The plug hole had a fancy mathematical name, a singularity. Hawking was excited and mystified.
In 1965, Roger Penrose showed that if a star collapsed below a certain critical radius, it would inevitably develop a singularity, at which time would come to an end. At first, I didn't understand either the significance or the proof of this result.
Hawking became obsessed with understanding the singularity. It was a poignant choice of specialist subject. A young man who'd been told he had 2 years to live was wrestling with a point in space where the universe disappeared out of existence. This was typical of Hawking's stubbornness, refusing to accept the limitations of his body or his brilliant mind. And even in his private life, he exhibited the same bravado. Despite his family's concerns over his health, he met, fell in love with, and married Jane Wilde, a languages student. As Jane later remembered in an interview, death seemed to be all around. It was the time of the Cold War with Russia, an age of defiance.
It wasn't a terribly difficult decision to take to marry Stephen, because I think a lot of people have forgotten that at that time, every day one read reports in the newspapers that nuclear war was likely to break out in the next year or two. People were saying they weren't going to have children because there was going to be a nuclear war. And the fact that Stephen had been diagnosed as only having a couple of years to live didn't really seem to be very much different from the situation that was facing the rest of us anyhow.
But out of this gloom, Hawking managed to conjure up light. Out of what seemed to be the end of everything, he found a beginning. Penrose had shown that bits of the universe could be sucked into a singularity, a tiny plug hole at the center of a black hole. Hawking took Penrose's equations and reversed them, like running a film backwards. Where Penrose showed the universe disappearing into a black hole, Hawking showed it came from one. For thousands of years, man had wondered how the universe began. Now a young PhD student from Cambridge had come up with an answer. It was an incredible turning point in our understanding of the world. But Hawking's results raised as many questions as they solved. It seemed to many that this inexplicable, sudden appearance of the universe, expanding out from a microscopically tiny point, had to be a miracle.
Is that God shows how the universe began, for reasons we could not understand. At a conference on cosmology in the Vatican, the Pope told the delegates that it was okay to study the universe after it began. But they should not inquire into the beginning itself, because that was the moment of creation and the work of God. I was glad he didn't realize I had presented a paper at the conference, suggesting how the universe began. I didn't fancy the thought of being handed over to the Inquisition, like Galileo.
Hawking's response to his results was to decide that the equations he'd used, Einstein's theory of relativity, were not the whole story.
General relativity makes a prediction that the universe was once infinitely small, but it loses the ability to describe the universe when it was tiny.
Hawking now knew that our entire universe did start out as a tiny dot. But he wasn't going to be happy until he could describe how that dot came about. Hawking had lain down a huge challenge for himself and the rest of physics. As physicist Michio Kaku explains.
The bottom line is, Einstein's equations are useless at the instant of the Big Bang. We physicists say that long time ago, the universe was so small, it was smaller than a basketball. You could put the universe in your pocket. It was smaller than an electron. Some people call it a singularity of infinite gravity. Now, that's silly. There's no such thing as infinite gravity. It just means that we use the word singularity to hide our ignorance. We don't know what the singularity is.
Unraveling this singularity, this tiny point of creation, became Hawking's life's work.
By tensing that one muscle, he can do everything from checking his email to speaking to browsing the internet.
Yes, the three...
I was there with him when he changed from using the finger switch onto the blink switch, and it was quite a... well, the blink switch sat in a cupboard for 13 years before he would even think of trying it, so he tends to go with what he knows.
Every time he changes to another type of technology, he seems to see that as admitting defeat. So he's very resistant to changing to other technologies.
Can you finish in 10 minutes?
In 10 minutes, 15, maybe.
It becomes very apparent that his struggle is daily. It's not just some...
But Hawking is nothing if not determined. And back in the 1970s, he set his sights on solving the big problem. What happened at the moment of creation? In the early 1970s, black holes were the agents of death, the place where everything we know about the cosmos came to a chilling end. But to a young physics researcher like Stephen Hawking, they were an exciting challenge. He'd already shown that the universe arose from a single tiny point. Now he wanted a complete theory of everything, a theory that would describe the moment of the universe's creation in precise detail. And again, black holes would point the way.
My own work on black holes began with a eureka moment while getting into bed in 1970.
In 1970, getting into bed was a protracted business for Hawking. His paralysis was increasing, and he needed constant care and attention from his wife, Jane. And they'd started a family. But despite his disability, the couple were managing. He'd taken a research post at Cambridge University and was eagerly pursuing his quest to understand the universe. Hawking was about to attempt something no other physicist had ever achieved. For 50 years, physicists had failed to unite the theories of the very big and the very small. Einstein's theory of gravity would not fuse with the very different theory of how atoms work, quantum mechanics. But what Hawking had glimpsed was a point where the two must clash, at the very edge of a black hole.
What happens if you have a black hole which is sitting there? It's black. That's why it's called a black hole. No light comes out of it. What happens if you include the effects of quantum mechanics?
Einstein's theory said the black hole was a smooth, perfect sphere. Hawking plunged it into a sea of particles and atoms. The two theories sputtered and fought each other. Somehow, Hawking must bring them together.
The problem of reconciling Einstein's theory with quantum mechanics is one of the holy grails of modern physics. What Hawking did in the early 70s was he didn't try to solve this problem completely, but he tried to put quantum mechanics and general relativity together in a very limited fashion.
What was all the more remarkable was that now unable to write down long equations and calculations, Hawking had to imagine the whole process in his head. As well as space and black holes, Hawking had to visualize a world we are all unfamiliar with. The bizarre realm of the very small, of the atom.
A good way to think of an atom is a bit like our solar system. You've got a nucleus at the center, and you've got electrons whizzing around. Now, let's imagine that this marble is the nucleus of an atom. An electron will be the width of this hair. Now, again, we're used to seeing in textbooks that an electron is more or less this distance from a marble. But it's not. It's not this far. It's not this far.
Force fields, they shimmer. Physicists often describe them as waves. Water, sound, and light can behave like waves, but so too can the parts of the atom. And that means they can spread out to be in more than just one place at a time.
Common sense says that when I fire this gun, one ball hits one target. That's it. If this is an electron gun hitting many targets, I find out that one electron has a probability of hitting many targets at the same time. Now, that violates common sense. I thought it was one ball, one target. In the quantum world, common sense is violated. Common sense has no place in the quantum world.
Hawking knew that atoms were not like little billiard balls. They turn out to be much more fuzzy and erratic. How could he join Einstein's stars and planets that float sedately along nice curved lines with atoms that buzz around in a frenzy?
At a very tiny level, our universe is like a crazy dance of waves, jangling to a myriad of beats. Particles appear and disappear at random. And at this level, nothing is certain, not even existence.
The theory of the very tiny says space is never empty. At an atomic level, there is always a tiny, tiny amount of activity. But the theory of the very big says nothing exists at the edge of a black hole. Hawking realized this was where the two theories clashed. He had to find out what was really going on. According to the theory of the very tiny, in empty space, there are pairs of subatomic particles that emerge out of the void, exist for a tiny moment, and then destroy each other.
And so the idea is that out of nothing, if you like, a pair of particles is created and then exists for a short time and then annihilates. And that's happening throughout space. So it's happening there, and it's happening there, and it's happening there.
Hawking realized that the positive particle would have just enough energy to escape the black hole, but the particle with negative mass would fall in. And it would do something extraordinary to the black hole.
Particle that goes inside the black hole eventually decreases the mass of the black hole. It effectively has negative mass, but the particle that goes off to the distant observer is there observed as part of radiation.
Although we now understand why black holes have to give off thermal radiation, it came as a complete surprise at the time. At first, I thought I must have made a mistake.
But Hawking had not made a mistake. Around a black hole, is an almost imperceptible microscopic glow. Positive mass particles fly off from it, behaving just like heat. Negative mass particles fall in. Slowly, almost imperceptibly, they decrease the mass of the black hole, and this eventually has catastrophic consequences.
So, what the Hawking result implies, it means that the black hole, instead of being black, is actually always emitting radiation. What is happening is that for most of its life, the black hole is gently sizzling away, but eventually it gets smaller and smaller, the temperature gets hotter and hotter, and eventually it gets to a point where it's so hot that it essentially explodes. It loses all the rest of its mass in a very, very short time.
Hawking had transformed the black hole from a ball of nothing into a galactic monster that chews up the universe and spits out fire and brimstone.
When black holes were first thought of, and when I first started studying black holes, even I remember thinking, oh, a black hole, it's the end of everything. A star collapses down and everything disappears into it, and nothing ever comes out, so maybe it's really boring. But really, black holes represent our best way to have an ultimate test of the physics of understanding the universe.
And astronomy has borne out Hawking's discovery. Black holes now seem to be where it all happens. They're the engines that rip up the cosmos and create new stars and jets of energy and matter.
Black holes are not ultimate endpoints. They really are beginnings of something, because around a black hole you have enormous amounts of activity going on. You have stars being ripped apart, and you have disks of accreting matter swirling around. You have cauldrons of heat and light around a black hole. You have jets being produced by a black hole. You have particles coming out at half the speed of light being shot away from a black hole. You have stars being born around a black hole. There's an enormous amount of stuff going on caused by the fact that that black hole is really there. And that's exciting.
Hawking had taken a great leap forward in his quest. He'd linked the theories of the big and the small for the first time ever in physics.
What was really amazing about this paper, really one of the most beautiful papers in the 20th century, is that his argument that this could happen relies on almost no assumptions. The assumptions about the nature of quantum mechanics and the nature of general relativity that basically every living physicist will agree with.
But Hawking had done more than just show that black holes were complex. The theory of the very tiny was starting to unlock the secrets of the very large. Could he now apply it to the entire universe? Could he now explain the Big Bang?
By applying quantum mechanics to the edge of the black holes in the 1970s, I was able to revolutionize our understanding of them. To expand our understanding further, we need to bring quantum mechanics into the heart of the black hole.
In the 1970s, it seemed Hawking had only to wrest the key to the universe from the inner reaches of his brilliant mind. But more humble problems of health, love, and fame would try to tempt him away from his devotion to physics. This world that is so familiar, how did it come about? Can we ever discover how all this came to be? Stephen Hawking runs a department that is still trying to find the answer.
He has his PhD students and they have supervision and they come in every week and they have lunch and they talk about ideas, and if they get stuck they can come to him. You have to have exceptionally good students to be able to cope with the heavy work that they have to have, and also with the communication. They really have to know their subject.
How have you all survived the summer?
Very well.
Start.
Go.
Aged 66, when many are retiring, Hawking shows no sign of giving up his quest.
The food's improved since I was a student. Has it improved the work rate of the students?
No.
I think it's quick there. I think it's in best proportion.
Hawking's life's work has been to come up with a theory of everything. A theory that explains how our universe works and how it arose. In the 1970s, he had huge success using the theory of the tiny quantum mechanics to better explain black holes. But in the 30 years since, using it to explain the entire universe has turned out to be just a bit harder. Hawking has admitted that he was overconfident. The early 1960s idealism of his work and his personal life have waned somewhat. His relationship with his family was often strained by his drive to succeed. His wife Jane, interviewed in 1989, said despite her dedication, she struggled to cope with someone whose whole focus was physics.
His determination has now rather outstripped mine. I cannot keep up with him. I do think he tends to overcompensate for his condition by doing absolutely everything that comes to his notice. I'm not a scientist. I'm not an appendage of Stephen, as I very much feel I am when we go to some of these official gatherings. I mean, sometimes I'm not even introduced to people.
With characteristic stubbornness, Hawking pulled through. He'd needed a tracheostomy, which meant he completely lost his ability to speak unaided. The famous voice box followed soon after. Then came the book. Through it all, Hawking's eye was, and still is, on the prize. The theory.
Even though the job has been more difficult than one might have hoped, I think there is still every indication that there is a final theory and that we may get there, but it just proves much more complicated than we originally hoped.
It is, after all, the toughest job in science. Hawking's trying to peer back to 13.7 billion years ago, to the start of everything. His main stumbling block has been getting the theory to explain what the entire universe was like back then, when it was all compressed to a size smaller than an atom.
Although the universe is very big now, the observable universe is something like 13,000 million light years, the distance light has travelled since the Big Bang. We know that that entire region must once have been compressed into a very, very, very small scale. But of course, once the universe is compressed into a very, very small scale or a very, very high density, we know we are in the domain of quantum theory.
Using the theory of the tiny, Hawking has made huge progress in describing the birth of the universe. But there is one part that eludes him. He's found it impossible so far to describe how gravity must have worked at the moment of the Big Bang.
If we want to know what happened when the universe began, we have to have a theory that can describe gravity on a very small scale.
For the last 30 years, Hawking has struggled to find a way to describe gravity with quantum theory. But he has unshakable faith that the theory of the tiny will eventually win through. And he's not alone. Today, all of physics is racing along beside him. Incredible experiments are now being built in outer space and deep underground, which will try to probe deeper into the very moment of creation. There is excitement in the air, a sense that the problem of gravity in the early universe will be solved, and that a theory of everything is just waiting to be found. Whether he finds it first or not, Hawking is philosophical about his part in this great journey.
I was unlucky to get motor neuron disease, but lucky in almost everything else. I have 3 very attractive children, success in my scientific work, and a real sense of satisfaction at having achieved all this, despite the difficulties. Not many people can say this.
Is there anything you wish you'd achieved professionally, perhaps, that you haven't already?
I feel I have achieved quite a lot, but one would always like to have done more. In particular, I would like to have found a complete theory of quantum gravity and the early universe. Still, that wouldn't have left much for anyone else to do.